Good evening. This lecture I'm going to record for term 7 of process engineering students. So what we are going to work on, we are going to work on two problems. One is the pipe segment, how we design and model that in HYSYS, and the other is how we design the pump in Aspen HYSYS. So the version that I have in Aspen HYSYS is version 11 here. Let's come to the problem here for the pipe segment first. He says that we have some water inlet here, we have some water outlet, we have the properties of the water inlet at 25 degrees Celsius, the pressure is 2 atm, of course it is only one component, so the composition is 1, and flow rate is 12 cubic meter per hour, and we have the outlet water which is coming at a temperature of 25 degrees Celsius. We want to find out what is the outlet pressure and how much is the pressure drop in your pipe segment. For the properties of our pipe segment, it is the mild steel and the pipe length is 10 meter, the pipe schedule is 80 and the nominal diameter is 40 mm. So I will keep both of these windows open so that we can work in parallel. So the first step in HYSYS is you add your component. I click on add here and I need to search for water. Once you have the water type in, you can double click this or click add. It will automatically add into your component list. In the next step, I need to define what is my fluid package. According to my given problem, the fluid package is ASME steam. So you click on add and it will open up all the properties packages HYSYS has in it. So I select ASME and now I have defined my fluid package. You can also rename them if you like. You can also rename the list of the component if you like, but for now I'm going to leave it like this. So I have defined my component, I have defined my fluid package, so I'm good with the properties. The next is I need to enter into my simulation environment. Now there are two ways that we can link our energy and material streams in Aspen HYSYS. The first is I can define my material streams. For example, let's say I bring this stream into my solver. As you can see, it is light blue in color. This is indicating that I need to define its properties. So you double click this, it will open up a properties window. Here you can name it. For example, I name it as an inlet stream. And as you can see, for my inlet temperature, it is 25 degrees Celsius. I type 25, it is already Celsius. If you have different units, you can choose them. The pressure of my inlet stream is 2 atm. So I type 2 here and select the appropriate units. This is my atm. The next is my flow rate is 12 cubic meter per hour. So I just type in 12 here. The units are already cubic meter per hour, which is good. And then you go to your composition and define your composition. Because it's only one component, I type in 1 here, hit enter, and it will open up a window where I can just click on normalize and click OK. Now I have defined my material stream. I can close this window. Now you can see that I have the blue screen, blue color of my inlet stream, which is indicating that all the properties of the stream have been defined. Now similarly, I can define my outlet stream and work with the energy stream as well. So let's bring my pipe segment. This is my pipe segment here. I just click it and bring it here. I double click this pipe segment. As you can see that the pipe segment is asking me what is my inlet stream, what is my outlet stream, and the energy stream. So if you have defined your inlet streams, you will just click it here. It will ask you what is your inlet stream. Now just keep in mind, this will also be available on your outlet stream as well. So this is why I prefer to use a different method in defining the streams. What I do, let's say delete this. The other method is more appropriate, I believe. So you can define your streams on the equipment itself. So here I give it a name of inlet stream, let's say. You can provide any name based on your system. As you can see that it has created a new stream. Similarly for outlet stream here, it is up to you whatever way is more convenient for you. Either you can define the streams already, bring in your equipment and link them, or you can bring in your equipment and develop your streams. There's no difference in the calculations. So once I have defined my material in, material out and the energy, now I have pipe segment defined here. Now before I proceed, you must notice here we have the yellow line around my pipe segment. This is an indication in HYSYS that we are missing some information with HYSYS simulation of pipe. So if we have defined inlet stream, outlet stream and Q, now we need to work on the properties. You will go to the worksheet. Now this is my inlet stream. As you can see in the problem, I have the temperature of 25 degrees Celsius. So I define my temperature, which is 25 degrees Celsius. My pressure is 2 atm. I enter 2 and then select atm. My composition is 1 and my flow rate is 12 here. So this I have defined here. We can along with this, before we move to the composition, we can also define our outlet stream. So let's see what are the properties for outlet stream. In the outlet, I only have 25 degrees temperature, so the outlet is 25 degrees temperature. You cannot define pressure because that's what we want to calculate. So I enter 25 and hit enter. Now I go to my composition and press 1, hit enter. It will open a window where it is asking me what is the mole fraction. It is one component, so it will be 1. You click on normalize and press OK. As you can see now, HYSYS has the information about my inlet stream and the outlet stream. Now in order to model my pipe segment here, I need to provide it some more information. So for that one, you go to your rating. On the sizing, you just click on append segment. Now this is where we will define these properties of our pipe segments. So for example, the length which is given in my problem is 10. I enter 10 meter here. Now because we are dealing with the horizontal pipe, we don't have any vertical pipe. This value will remain 0. If you have any vertical pipe, then you will provide the values here. And then we go to view segment. Now before I go there, the material is the mild steel, which is already here. If you have a very different material, you can choose them based on these properties. And then you click on the view segment. Now this is where you provide the schedule number for your pipe. In our given problem, it is 80 here. So we click on 80 and the nominal diameter which is given in our problem is 40 mm. So I go to here and choose my 40 mm. As you can see that I have the green bar with the OK signal. This means HYSYS has simulated our pipe segment. Now before I jump into the results, I just want to show you how does the figure looks like. So as you can see here, that yellow line has gone. This means HYSYS has simulated my equipment. If you see the black lines with this means our results are ready to analyze. And how did you analyze your results? You go to the design tab and then you go to your parameters. This is where it is indicating me the drop in pressure. So our first objective was find out the pressure drop. So our pressure drop for this system is 25.34 kilopascal and with the required duty of 280.9 kilojoule per hour. In our problem, it was also asking what is the outlet pressure. As you can see here, for the outlet pressure, you go to your worksheet and you go to your conditions, and this is the outlet stream and this is my pressure for the outlet, which is 177.3 3. As you can see that my pressure drop is 25.34 kilopascal. As we know from our process engineering background, if we have a material which has more roughness, there will be more pressure drop inside the pipe. So let's say I choose something rough concrete as a material of construction. As I chose this one, you can see that I'm going to design tab, and my pressure drop is 101.3 kilopascal, which is too high. That HYSYS is giving me an indication that it is exceeding your limits. So you can just play around and see how it looks like, and you can see that my pressure drop is very much significant. That HYSYS is giving me a signal here that this is too much pressure drop. So we cannot afford this much pressure drop because of the high cost. So we can change it back to mild steel or any other company. If you want to analyze how is the performance of your pipe segment, by that I meant to say with the passage of the length how different variables are changing. What you can do, you can go to the performance tab and click on view profiles. Now this is where we have all the tables and developed, and the graphs as well. As you can see that my length was from 0 to 10 meter. At the distance of each 2 meters, it is showing me how there was a drop in the pressure. There was no change in the elevation because we have the horizontal pipe, of course, but as you can see that there was a decrease in my pressure. So this was the pressure of my outlet stream, this was the pressure of my inlet stream. There was no change in the temperature, and we have the vapor, we have all as a liquid fraction, so the vapor fraction will be 0 here. This is the change in the heat transfer while the liquid was flowing inside the pipe, and various other factors. If you want to plot them, you can go to the plot, and you can see that there is no elevation. So with the change in the length profile, there is no change in the elevation. There is no change in the temperature. However, there is a change in the pressure. So the pressure drop, we have the maximum pressure at the start of the inlet stream, and it start to decrease because of the friction of mild steel material of construction. If you want to export this graph, what you can do, you just right click here and click on print plot. It will develop a PDF file of your graph, and for example I save it on my desktop. You can name it and save it anywhere, and you can just save it. And this is what I get it as an outcome from HYSYS. So there is a change in my pipe length with the pressure. You can analyze different graphs and you can see this is my liquid and there was no vapor, so you will not see any relationships here. So that's how we analyze our pipe segment. So now we'll move to the next problem, which is how we design our pump here. So I'm going to delete this system here. So now we need to work on our pump problem. So in our pump problem, we have the inlet water at a given properties of 55°C temperature, pressure is at 3 atm, and the flow is 120 kilogram mole per hour. Mole fraction is 1 because it's only one component. We want to find out what is our outlet temperature, and the pressure being 12 atm, and the mole fraction is 1. So let's see how we do it. Now in terms of defining the properties, because I have the water which I have already defined, so I don't need to make any changes. The fluid package is the same, ASME steam, that's what we used in our previous one. So from properties point of view, we don't need to add anything into the HYSYS for the pump problem. In terms of the simulation, you click on the simulation and we need to bring in our pump here. This one is before I take this, I should have mentioned it in my pipe segment. So you can change the views if you are not comfortable with the figures only. Let me open this. As you can see here, I click on this detail icon and it is giving me the names and everything. Or you can click on compact view and it will provide you a compact view. So let's select my pump here. I bring it into my solver. Now I just want to keep some space before we can see that. So we double click on our pump here, and from our now we can define our inlet stream. Let's say I say it as water inlet, and for the outlet I will say water outlet, and we are providing it the W as energy. Let's say, as you can see, once I enter these properties, HYSYS has linked different streams with it. However, the color of this pump is still yellow. This means we have not provided all the things that HYSYS needed. So let's go to the worksheet. Now in the inlet, water inlet, I have the temperature of 55. I place 55 degrees C. Now keep in mind there is a difference between a compressor and a pump. Pump is only used when we have the liquid. So you cannot add the vapor fraction when you are designing a pump. So my properties of the inlet stream is 55 degrees Celsius. My pressure here is 3 atm. So I enter 3 and choose the unit of atm. My molar flow rate is 120 kilomole per hour. This is my molar flow, which is 120 kilomole per hour. Now in terms of my outlet streams, I have our temperature is what we need to find out. However, I do have the pressure, which is 12 atm. So I select 12 here and go to my atm. I have provided my outlet pressure now. Then you go to the composition and provide the composition. I enter 1 here, hit OK, then normalize. It's only one component and it will be OK now. As you can see that HYSYS has given me OK as a green signal. So I have defined all the properties and HYSYS has solved my pump problem here. Now let me maximize this. So this one I have defined my water outlet. This is my pump here. This is my water inlet, and this is my energy required for this. Now, in order to analyze your results of the pump, you can first identify what are the properties of your outlet stream. My temperature there is a slight increase in the temperature from 55 to 55.1 degrees Celsius. There is a significant increase in the pressure, of course, because it's a pump, and there is no change in my molar flow here. So these are the properties of your streams. The most important is you go to the design tab, and under the parameters, that's where you have the delta P calculated. So that's where you see your delta P, which is 911.9 kilopascal with an adiabatic efficiency of 75%. And the duty here is 0.740876. This is what our duty of the pump. We can also work around and see how different scenarios can affect it. For example, right now I know that my outlet temperature is 55.11. If I delete my efficiency here and I go to my worksheet and I give it a temperature, let's say I'm saying that my outlet temperature is increased to 60 degrees Celsius. I hit enter after entering 60 and then go to the design tab. Now you can see that adiabatic efficiency has been significantly decreased to 4.27%, and this is my delta P in this case. So you can just play around with the different parameters and see how they are affecting your analysis and how you can work around. I hope this helps. If you have any questions, you can email me. Thank you.